I want to make a quick video about something that might be useful to you. We've probably all had this happen, or maybe you haven't, but this will probably happen to you in the future if you're building amps. You're on eBay, you see something like this, and it's just like as is $10 or something like that, and you're just like, oh, you know, it looks like a pretty good transformer. I have no idea what it is, and you just order it, right? And so you end up with this mystery transformer. It looks like it's in good shape. You know, maybe the listing said power transformer of unknown origin or something like that. Now, I had a friend send me this, and he told me it was a power transformer. And so I know it's a power transformer. I could probably have guessed that by looking at it. But maybe you've got an idea. You've ordered something on eBay, and it's supposed to be a power transformer. It's supposed to be an output transformer or something like that. But you just don't know anything else about it. And you just want to sort of map it out for use in a future project. And so that's what I'm going to show you how to do today. Now, there's going to be a little bit of guessing involved in this, but this will give you a lot more to go on, sort of to use this transformer design process. And so the first thing we're going to do is we're going to draw out the windings. Okay. And we know that because this is probably a power transformer, that we're going to have a primary winding, and then we're going to have some secondaries, right? We've got some unknown sort of other wires here of different colors. And we've got two here that are black and two that are yellow, so we can sort of guess those are going to be part of windings. But then we've got some like striped ones here, and we've also got a red one. Okay, so we're not really sure about those. So the first thing we're going to do is we're going to test for impedance. So get your meter, and we're just going to see what, I don't want it on the one that beeps because that'll be really irritating. So we're going to have the one that doesn't beep. Let's try these black ones first. I have an inkling that those are the primary side, because that's sort of the color code is usually that, black. So let's just go ahead and hook up here and see what we got. And you can see that those are indeed part of the same winding. If they weren't part of the same winding, they would have no continuity, or they would have some mega ohms or something like that. But what we have here is 4.4 ohms. Now I know my leads are 0.2 of an ohm, so I can subtract 0.2 of an ohm and say that the resistance here is 4.2 ohms. And so I'm going to go ahead and just take a guess and say this is our primary winding. And we might find out in the future that it's not our primary winding, but we'll figure that out after this. So we're just going to draw it in here. We're going to say 4.2 ohms. Right? Good. All right, now let's try and see if we can figure out what the secondary is looking like here. So I see these are both yellow, so I'm going to assume they're part of the same winding here. So I'm going to go ahead and connect yellow and yellow. And we get 0.4 of an ohm, so that's an extremely low resistance winding, right? And so a very low resistance winding means it's going to be probably high current winding. And so we can assume that this is probably a 6.3 volt winding, or maybe it's like a 5 volt winding for a rectifier or something like that. And one of these other things may be the center tap of this. So let's have a quick look and see if we take one of these off and we connect it to, let's say, this red one. So there's no continuity there, so the red is not part of the yellow. How about the red and yellow? Okay, no continuity between red and yellow. How about green and yellow? Yes, so green and yellow is 0.3 of an ohm. So we know that yellow and green and yellow are part of the same winding. Let's just guess for now. Now we might find out this is wrong later, but let's just guess for now that the green and yellow is the center tap of the yellow, because that's usually how it goes. So let's go ahead and draw that in. Like this, and we'll do a center tap here. And so we'll just say, yeah, so black, should have done that here, black, yellow, yellow, and then this is what, green, yellow. So green, yellow, and green, I guess. We'll just do like that, right? And what did we say was between our yellow windings here? It's a really, really low impedance winding, so I know it's, you know, my probes are 0.2 of an ohm or something, so it's 0.2 2 ohms here to here, right? Good. And what we have left here is then, it's going to be, we only have 2 wires left here, so it's going to be the red and the red and yellow. It's going to be our last winding. I assume there'll be continuity there. Okay, and so this is a 16 point, so we know it's got 0.2 of a thing we got to take off there, so it's going to be 16.7 ohms. Okay, so it's red and yellow red. We've got 16.7. Good. So we basically got this in a place. You notice that has a pretty high resistance. I can already tell you this is going to be the high voltage winding. How do I know that? Well, it's about the ratio. So the more turns you have compared to the primary winding, the higher your voltage ratio is between here and here. And we're going to find this out in a second because we're going to be hooking this up to like 10 volts. So we're going to be looking at the ratios. But you can see that having such a high impedance means there's a lot of turns here. There's a lot of copper right in there, and it's probably a thin wire. And so you get a higher resistance on the high voltage. All right, so next thing we're going to do, we've got our variac here. We're going to hook this up to our likely primary here, which is black. Now be careful doing this, all right, because if you put 10 volts here, on the high voltage winding, you're likely to get, 70 volts out or something like that, 60 volts, something high. It's going to be a ratio. And so you pick a nice round number. You could pick 1 volt if you want to be really safe, although I want to pick 10 volts just so we can have a little bit more sort of accuracy in our ratios measurement, because if we pick 1 volt and you go to the 6.3 or the 5 volts or whatever we're going to discover this is, you're looking at a fraction of a volt then, which is fine. This will measure down to a fraction of a volt. So 1 volt, 10 volt, pick a round number, 1 volt or 10 volt. I'm going to do 10 volt, I think. And so let's go ahead and give it 10 volts in here. Got on the wrong setting here. We want this. All right, so I've got the variac all the way down. I'm going to flip it on. As you can see, even with the variac all the way down, it still gives us a little bit of voltage out here. So we're going to go up. So we could stop at 1 volt there. Maybe that'd be smart. Now, I should have told you, make sure none of these little guys are touching, and also don't touch them with your fingers while you're doing this. All right? We'll be turning off the variac between, we're not going to touch this when it's live like this. We're going to bring it up to 10 volts. Okay? Just get it as close as you can. In your variacs, you can't get it perfectly, or you can. Sometimes you're lucky. I'm going to flip it off. Right? Good. So we know we got 10 volts right there on the primary, which I assume is the primary. And we're going to go over here, and let's just get our high voltage out of the way. We got red and yellow and red here. So let's go ahead. Red and yellow and red. Okay, we're going to flip it back on and see what we get. So it's not that much. It's not that much. Interesting. So this might not actually be that high voltage of a transformer, which is just fine for me, honestly. Most old power transformers have a little bit too much voltage on a secondary. Now you can see we don't have a center tap on the secondary, so I can already tell you that this is not designed to work with a tube rectifier. A tube rectifier would need a center tap on the high voltage winding, and so this is going to be used with a sort of a modern sort of bridge rectifier, which is fine because a modern bridge rectifier will take the whole voltage of the winding and multiply it by around 1.4. And so we'll end up getting more out of this. So this might actually end up being perfect for a little preamp or something. In any case, we're getting 15.6 here. So 6, and this was 10 over here. This is going to help us discover our ratios. Let's flip it off again. Let's go down to our yellows. We'll check our yellows, and then what we'll do is we'll make sure that that yellow and green is exactly half of what we're seeing between our yellows, just to make sure that it is our center tap. We might be surprised. Maybe we'll surprise ourselves and it won't be the center tap. We'll see. All right, so let's see. All right, so we've got 0.61. We'll just say 0.6 of a volt here, and then we'll flip it back off, and we'll take one of these leads and go to the yellow-green right here. Back on. 0.3. All right. So this is going to be 0.3, 0.3, just like that. So the yellow-green is the center tap of the yellow and yellow. And so now all we got to do is find out our ratio. Since we picked a nice even number of 10, we just move the decimal point over, and we're going to have 1, and over here it's going to be 1.5 to 1, 1.56 to 1, 1.56. So it'll be 1 to 1.56, and down here we're going to have 1 to, let's see, we're moving it over 1, and so it's 1 to 0.03, or 0.06 over here, so it's 1.06. And so now all we have to do is multiply these by 120 to find out what our voltages are going to be. Sorry, we're going to do 1.56 times 20. So this is going to be a 187 volt. That's AC RMS, of course. And then down here we've got 120 times 0.06 equals 7.2. So already you can see we got a problem here. 7.2 is not a typical voltage. So probably this was designed for 115, right? So let's try that. Times 0.06. And now we're at 6.9. That's closer to the 6.3 that you would expect. So we just got to keep an eye on this. If we decide to use this in a modern circuit, we could put a resistance or a thermistor in line here, which would drop a little bit of the voltage. You could put some resistance in series with this, drop a little bit of your voltage, or you could rectify it and regulate it down to 6.3 or whatever. It may droop down to closer to 6.3 when it's loaded down. And that's what we're going to talk about now, because now we got to try and figure out, we know our voltages, roughly. We got to figure out what kind of power we can expect to produce with this transformer. And so the first thing you want to do here is guess. You just kind of look at it and you pick it up and you think, you know, it looks about like a 30 to 40 watt transformer. So we're just going to expect 30 to 40 watts just based on the weight of it, the look of it. Now that doesn't tell us anything about the individual current capabilities of the windings, but it does give us a ballpark of what the total power should be out of something like this. And I can just tell from experience that this is somewhere in the 30 to 40 watt range as far as power transformers go. And now the next thing you want to do is you want to assume 5% or so regulation of the power that comes out. So what this means is that if you put 120 in and unloaded you get 187 volts out, you want to assume that under full load it will only droop by about 5%. Okay? And so 187, that's what, like 8 volts or something like that, 9 volts, 8 or 9 volts or something like that is what you would expect this to drop over from where it is when it's loaded down to its sort of maximum current. And you can also calculate that. So if you use Ohm's law, you've got a resistance of 16.7 ohms. You want to calculate the current for a drop across that of about 9 volts, something like that. And you're going to end up with a milliamp rating that you can sort of then apply to this winding. So I'm going to do that really quick. Okay, so I was sort of doing the normal math on this, and I'm getting something that's well in excess of what you would expect. And so it may just be that this winding, I guess what I'm trying to say is that if you take the 8 volts or so and you divide it by this resistance, you come up with some hundreds of milliamps, right? And you know that this is not going to provide hundreds of milliamps and 187 volts. Because the core is just not big enough to support that kind of power. And so probably this transformer has a sort of a higher gauge winding here to improve the regulation of the output voltage. And so let's assume something more like, like a 4-volt drop or something like that. And so we'll do 4 divided by 16.7 equals, and that gives us something like, still it's giving us a couple hundred milliamps here. And so let's just assume this is going to be like a 200 milliamp winding here. So like I said, there's sort of guesswork here. 200 milliamp. And so you can also say like 200 times 187 times 0.2, right, for power that we're going to draw here. So it's 187 times 0.2 equals, we're already at our maximum here, basically at 37 watts. So that would be 37 watts here. And that's not even calculating in the heater winding, which is obviously going to need to run, probably a couple of amps there to run the power tubes or whatever it is we're going to do with this thing. And so let's now do the math here. We're going to assume, like for this, it's going to be a fraction of a volt drop or something like that, to be 10% of this, right? And so let's just assume a loaded drop of 0.1 of a volt or something like that, and we've got a 0.2 ohm winding, and so it's going to be 0.1 divided by 0.2, and that gives us 500 milliamps, and so it's going to be more than that. So I'm just doing something. So like I said, this is sort of guesswork, because this is going to supply at least a couple of amps, right? And so maybe that's why our voltage was so high out here. Maybe this one is meant to sort of droop a little bit. So if we assume that it's going to droop down to 6.3, for instance, that's like 0.9. So we could do that. We could do 0.9 divided by 0.2, 0.9 divided by 0.2 equals. And so that gives us 4.5 amps. And so that's probably closer, but that's a little bit much probably for this transformer. So let's just split the difference there and say this is probably going to give us something in the 3 amp range. And so 3 amps times 6.3, 3 times 0.3, that's going to be another 18 watts, right? 18 watts. And so you can see that if we do 18 watts here and 37 watts here, we're up here, we're exceeding our guesstimate of this transformer, right? And so you can probably assume to pull a little bit less. That might be like absolute maximum rating or something like that. We're going to decide we're going to pull a little bit less than 200 milliamps here and 3 amps here, like in the 150 range, and maybe in like the, you could probably get 3 amps out of that, but maybe like more like a 2.5 or something amps out of that one. So I know that is maybe not as scientific, it's maybe not as exact as you would like, but it's a hell of a lot better than just like having no idea what to do with your transformer here. And so that's that. If you got a mystery transformer, you can sort of analyze it like this, and you can kind of guess. You can use your best judgment and do a little bit of measurement, and you can see voltages you might expect and the current ballparks that you might be able to use for this transformer. And then obviously the proof of the pudding is in the eating, and so when you get a circuit ready to go for this thing, load it down and see what happens. You don't want your transformer to get up above, if you're getting up into 70C territory, if you're getting up into 70C territory, you're getting too hot. So you're going to shoot for power draw from this transformer that keeps it below probably 70C or something like that. 70C is hot. You touch your finger at 70C and it's going to burn you, right? And so somewhere in the 60, 55, 50C range is going to be a better sort of operating point for a transformer like this. Obviously, if you get excessive drop, you've loaded the transformer too much in the circuit, right? And so if you load this down to 200 milliamps and suddenly the heating, the coil heats up and the resistance increases and it starts to dissipate a bunch of power, and this voltage drops a bunch, you've loaded it too far, right? And obviously, when you exceed the ability of the core to transfer power, then all bets are off, and the transformer can get quite hot, and your voltages will drop, and all of that kind of stuff if you've saturated the core. So that was a quick little video on how to analyze a mystery transformer, and thanks, Caleb, for sending me the mystery transformer, and I'll definitely use it for something. It seems like a really good transformer for a little preamp or something, and so I will use it as such. All right, that's it. Thanks for watching.